Welcome to episode 3 of the Analytically Speaking podcast series. This episode will discuss the future of chemometrics, data-driven measurements, and portable instruments for chemistry. I'm Jerry Workman, the Senior Technical Editor of Spectroscopy, and your podcast host. Thanks to our listeners for joining us for a deeper look into all things measured with light. Spectroscopy is the study of the interaction of electromagnetic radiation, commonly referred to as light, with matter. In this episode, we have the pleasure of speaking with Dr. Karl Booksh, a professor in the Department of Chemistry and Biochemistry at the University of Delaware, where he teaches and performs research in the area of analytical chemistry. Karl's research interests encompass many aspects of analytical chemistry, including Raman and Raman imaging, laser-induced breakdown spectroscopy, also known as LIBS, fluorescence, portable chemical sensors, miniaturization of analytical devices, and data-driven science, incorporating many chemometrics and data analytics techniques. He is the author of over 100 peer-reviewed articles and is an American Chemical Society Fellow and a Society for Applied Spectroscopy Fellow. We are pleased that he is here with us today. We have invited Karl to our Analytically Speaking podcast to discuss his research on the development of portable chemical sensors for environmental, biomedical, and industrial process monitoring. His research is predicated on the belief that it is better to build small chemical sensors capable of reliable measurements in the field or in process applications than to collect samples for future laboratory analysis. He is currently organizing a National Science Foundation workshop entitled Data-Driven Measurements and Instruments for Chemistry. Karl, thank you for joining us today.
Thanks, Jerry. I appreciate the invitation.
Well, we'll get right into it. So how did the interest in developing an NSF workshop on chemometrics and data-driven measurements and instruments with leading practitioners come about?
Thanks. That was really a NSF-driven request. And, when a funding agency requests something, it's kind of hard to say no. So kind of what's part of the problem is, if I understand it correctly, is Professor Barry Lavine and I sent a number of proposals to get funded, and first year we had a really hard time even getting it reviewed. And part of the reason was that I guess the bench of the Rolodex of people doing chemometrics and data analysis in NSF, chemical measurement and imaging, was a little bare, and I guess they'll maybe even a little self-critical. So it's really kind of hard to get good. The NSF was the program officers having a hard time getting a robust panel of reviewers. So what they asked was that if Barry, Sharon Neal, and I would pull together a workshop to try to help chart out what the future of data analysis in this area of chemistry is, with the idea of both sort of informing, pulling together the wisdom of the crowd of the field and informing future researchers what might be some promising research directions, and informing NSF of what are some good ideas to keep your eyes open for when the right proposal comes along. So, it's a really fun opportunity for me just to bring together a lot of people that are smarter than I am in many different ways, and get to try to distill their wisdom into a document soon that will hopefully kind of guide the field for a bit.
Well, that sounds very interesting. I hope we can have access to that document and take a look in the future.
Oh yeah, when these are all public domain, once they get written, NSF publishes them on their website, and you can request it through any the right government channels. They'll be on the web.
Wow, that sounds great. So what exactly is your definition of chemometrics, and why is chemometrics important?
I get that question a lot. And in a way, the way I get it most often is what's the difference between chemometrics and machine learning? Because, machine learning's all the rage these days. And it took me a while to kind of come up with what I think is the concise definition is, and I would just say chemometrics is machine learning with domain knowledge. A lot of the lot of the field of machine learning, well, I've, you know, I've always sort of only half joked that it's a lot easier to teach statistics to a chemist than it is to teach chemistry to a statistician. And so that's kind of where the chemometrics comes in, is what do you get when you can hopefully be better than average in both your knowledge of chemistry and your knowledge of data analysis, and make this become a symbiotic relationship with how you approach the collection and the analysis of data to really learn new things about chemistry. Too often, to me, statistics and machine learning gets bogged down in the mathematics and not the practicality of the chemistry. Whereas the chemists, without the machine learning knowledge, might not be able to pull the subtle chemistry out of all the data. So chemometrics is combining these two skill sets to hopefully make the sum of the whole greater than the sum of the parts.
Well, how would you respond to the question, and what is the state of the art for chemometrics today?
Oh, that's a hard one. Um, at the risk of offending the entire European continent, I fear that the state of the art is not good, and because we seem to be bogged down into not thinking much beyond some version of partial least squares, and that, at least I get that a lot, out of a lot of the papers. It's not coming up with something truly new. It's coming up with a couple of new letters to modify the algorithm of partial least squares or some other classical chemometric strategy. So I think that I would say the state of the art is we're at a crossroads where we really need to decide whether we become a dead science like liquid chromatography or gas chromatography or flame AA, where there's really not that much going on because it's well established, or whether we want to really move forward in embracing, in this case, a lot of the new statistical things in machine learning, Bayesian statistics, and much more complicated methods to bring those into with domain knowledge to come up with a new paradigm of how chemometrics is applied in chemistry. So there, I think with that, I think I just offended like probably 2/3 of your listener base.
Well, you're planning to convene a workshop, and I quote, to explore research opportunities in chemometrics and chemical applications of other informatics technologies for exploratory and multivariate analysis in order to construct a roadmap for future research. What are some of the greatest challenges for measurement science that chemometrics can help solve?
Good question. So looking to the future, um, I think there's a lot of challenges out there that I don't fully have my head wrapped around, because we're in that we now have the capability to collect massive amounts of data. So how do we sort through the massive amounts of data and really pull the information, the chemical information out, separate it from the noise, to learn something about the system we've been observing? And so on one hand, that's forward looking at what we could do and do better. But again, and that's how we could look at where chemometrics, and I'm going to call it passive measurements, in that we're studying what happened. I think where another place where chemometrics will become more and more valuable is could become more valuable, we haven't done enough with, is how do we use it to come up with new chemistries, new pathways, new things we could do in the future, designing new materials. Another way that I think it could be useful, and that's been underappreciated or underapplied, is studying and using it to understand dynamic processes. And so I know it kind of sounds like kind of a redundant, but think of a process that changes in both time and space. We lack the oftentimes the sense the comp not the computational power, the sensing power to be able to monitor this a whole process with the temporal and spatial resolution we need. Normally we choose both either temporal resolution or spatial resolution. But how do we use mobile sensors with a dynamic sensing strategy to move around and focus on where the chemistry is going to happen or the chemistry is happening when we really don't know where the chemistry is happening a priori or where it might be happening a priori. And I think right there, that to me is going to require a really strong dynamic relationship between the chemometrics, the data analysis, and sensor development in the future to intelligently, monitor dynamic processes or exploration. Imagine if we're going out to explore Mars and we have like a swarm of sensors. Right now, we're doing it with just like one Mars rover on a grid search. But how could we have a swarm of sensors and maybe sensors of different types all working in concert to really understand what's going on in a interesting in an unknown, interesting, and changing chemical environment?
Well, so what are the mathematical and software tools that are the most important when performing chemometrics analysis?
Wow. Even though I did harsh pretty much on partial least squares, the basic things, partial least squares, linear discriminant analysis, um, I think can get most people through 95, 99% of the applications that we normally encounter that require either calibration or classification. Um, the question then is, what are the tools that will win the future when we start developing new applications that can't be solved with established methods? Um, that I don't know. I think there's going to be lot of research there, a lot of new things that'll come up. Uh, Deep learning, I think, is going to evolve a lot over time from where it becomes really computationally intensive to a becoming more facile for the average person to do, to really reach in and look at large data sets and uh, pull out knowledge. So I don't know what's going to be the tools of the future, but I think the tools that we have now really will get most people a lot of the way to a lot of what they want to go. Choose one or few the basic tools and use them well. And then that gets a lot of what you want to do. It's like building a house. You get most of the stuff done with a hammer and a screwdriver. It's just the special tools you need for more special projects.
Yes. Well, how can chemometrics be used not only for modeling, which many of our audience are familiar with, but also for discovery, for really gleaning that detailed information from gigabytes or terabytes of measurement data, from chemical or biochemical processes, or from the environment?
Oh yeah. So in a way, that's where things like I think where deep learning will come in. Where there it's ways of um, going through these gigabytes of data, starting to bring in ideas like variable selection, where you find out which of your observations are most relevant to describing chemistry of interest, and which ones are just describing noise. And so that's kind of the machine learning side of it. Now you get the chemometric side of it is where you start to look critically at these models and the results of the models, and you ask yourself, do they make chemical sense? If you're trying to determine different species of trees, with a by handheld LIBS or something, and it comes out you're making your analysis based upon molybdenum isotopes. The the odds are your model is pretty spurious. It just happened to work for that one data set and probably doesn't rely much on the actual chemistry that's relevant.
Well, I heard one leading researcher state his concern that there's real problems these days with interpretation of data or in asking the basic question, what is the data really telling me? It seems that there's an alarming practice of repeating an experiment until one gets the desired results. What would you say to this concern?
So it sounds like you're not a fan of p hacking.
No.
Yeah. Um, oh, it is a concern. There's tons of, well, not tons. There's more and more papers talking about lack of reproducibility of the literature is a severe issue. I fear as long as our funding is going to be results based. Well, sorry, maybe not results is not the right, I guess that's the right word. Product. As long as our funding is product driven and not results driven, this will always be an issue. And what I mean by that is so much of the funding is based upon the quantity of the products you turn out, how many how many papers you get, how many talks you give, what journals are these papers being put in. That people will always have a perverse incentive to try to come up with some provocative, of getting enticed by the provocative results to get them in Science or Nature, and or to just get as many papers out as possible, which is where the kind of the p hacking comes in, um, to keep their numbers up, and this helps you get refunded. So it's something that us as scientists really need to watch out for. It's something that us as scientists need to police when we're reviewing papers and proposals. It's it's a serious problem. I think it's probably one of the major threats to the scientific enterprise that there is, because it really undercuts our credibility. I don't want to say the review process is broken in that. I mean, it kind of is, but I can't think of a better alternative.
Yes. I Are there limitations on the kind of data that can be analyzed using chemometric methods? And to follow that up, what are the real limitations and how important is initial experimental design for achieving an optimal result? And we note here that the optimal result is not necessarily getting the result you want, but is more in achieving the best truthful interpretation for the data you have.
What? So I guess that's a lot of questions to unpack. So,
Yeah.
what are the limitations of the kinds of data that can be analyzed using chemometrics methods? I honestly don't think there's any limitations because it's data, and so the whole idea of, I mean, I maybe the only limitation is a tautology. Well, if you're going to use chemometrics methods, it should be chemical data. Uh, but any sort of measurements or observations really could, you know, can be analyzed, should be analyzed. One of my initial thoughts was to say, well, you should have more data than noise. But my dads want to say that noise is just data you're not smart enough to handle, and I think there's a lot of information in the noise too. So I I wouldn't want to put limitations on what kind we can handle, can be analyzed. You just might need to come up with new methods to handle it. And so it may have been saying that. Let me take a step back, and we talk about traditional chemometrics. Traditional chemometrics, you're right. There's certain types of data it can handle, and they're almost the two implicit constraints are pretty much linearly additive data. So your effects are linearly additive, and your noise is normally distributed. So if you look at traditional methods, that's kind of the two assumptions that they have. But as we get to more and more sophisticated methods coming out of machine learning, we can really relax both of those constraints if they're done right. So in a way, the further we get away from linear additivity and normality of noise, the harder the data is to analyze and the more we need to use modern machine learning methods coupled with chemometric, with domain knowledge to give a new form of chemometrics. And this sort of loops back to, I guess, one of the things that will be discussed a lot in the workshop is how do we go about doing that? What are the areas where we really need to combine new machine learning or state-of-the-art machine learning with domain knowledge to develop new chemometrics? What's the rest? There was more to this question than that.
Well, yeah. How about experimental design? For example,
Yeah.
we've all seen data where a lot of conclusions are drawn from 20 process samples, as an example. So how important is experimental design in putting that teaching set or learning set together?
Oh yeah, what was the takeoff of the Longfellow poem of I shot an arrow into the air, it came to earth, I know not where. Dang, I lose lots of arrows that way.
Right.
um, so yeah, I mean that's always a problem. I mean that's been the bane of chemometricians ever since the get-go, right? You have an experimentalist, they'll go out, they'll collect a bunch of data, it won't tell them anything, and then they just dump, a few gigabytes, or in the olden days, a 3.5-inch floppy on the chemometrician's desk and say, fix it. and yeah, and so it's hard to do. Um, so yeah, the experimental design is the foundation on which the house is built. And so you without that really good foundation, it's not going to work. So you really, if you have convoluted variables, you have convoluted variables. You're not going to be able to do a good analysis. If you have uncontrolled variables that turn out to be very important, that can cause things to collapse. So you're right. You really need to pay attention from the get-go about thinking about what is the effects you're wanting to study, how do you isolate them, how do you control the right variables, and something else that I think we don't think about enough in chemistry is power analysis. How, given how big you think the effects are, and given what your assumptions about the noise distribution is, how many samples do you need to collect in order to observe this effect and show with any statistical confidence that it's real?
Well, let's shift gears here, Karl. Is that what are some of the applications in spectroscopy for the more advanced chemometrics methods?
For me, the one that I think is the most exciting is handheld chemical sensors. We're able to bring all sorts of chemical sensors, spectroscopic sensors now out of the field. I mean, handheld LIBS, handheld XRF, or the handheld XRF are almost ubiquitous in archaeological digs now. They're no longer bringing the samples back to the laboratory. They're collecting XRF spectra in the field. I think we could do the same thing with LIBS. We have now portable Ramans and portable IRs devices that can do soil samples and atmospheric samples. And imagine, again, we have this swarm technology where we could have drones all working in concert, each of which of them could have a small little, a couple of small gas sensors or MOSFETs or something that they're constantly sending. I guess those aren't spectroscopic, but they can have other spectroscopic sensors, even looking, that they could be sending data back to a central processing unit. So how do we handle all of this data where we are realistically working at the borderline, but we're working very near the signal to noise limit, and how do we do as reliable of analysis as we can for either both quantitative or qualitative methods right there at the signal to noise, where we're, instead of relying on a small number of really good measurements, that's what the laboratory people do. How then do we shift our gears and redesign our data analysis thoughts to how do we optimally do it with a large number of lower signal to noise measurements? And I think that's where I think that's going to be a lot in the future. That's where a lot of the stuff is we're going to going. Some sort of swarm analysis and field analysis where we're collecting more and more low resolution, low signal to noise data, but very rapidly. We're going to make up for with quantity what in the past we tried to do with quality.
Okay, Karl, could you say a little more about what was required to make instrumentation into handheld sensors and the chemometrics involved? Chemometrics used to require a lot of computing power. What's all happening in the smaller sensor world?
Well, from an instrumental standpoint or from an application standpoint?
Well, just the instrumentation and the data analysis software that goes with that.
Okay. Not much yet. At least not at the level where I think it could or should be going pretty rapidly. In that, right now, at least whenever I've gotten all the handheld instrumentations that I've been lucky enough to play with, either through loaners or purchasing, is they have a lot of effectively univariate classification models. I mean, they might rely on the whole spectrum, but they're going to quantitate or identify particular species. So they're oftentimes just wanting to build individual calibration models. In the case of the LIBS or the XRF handheld instrumentation that I have, that to look specifically at individual elements. It's like, here are the 5 major elements we want to look at in soil or in steel, and we have the models built in for the spectra to determine what's the iron content, what's the lead content, what's the sodium content. What I think we need to do is go to the next step and have in the software help with building broader models that are application based, not that are user based, not embedded based upon from the factory for quantifying or identifying specific chemicals, specific elements. For example, I've seen like FTIRs or whatnot, or portable Ramans, where they have the models in there for specific drugs. It's designed to identify, is this cocaine, is this heroin, is this, or a list of particular hazmat chemicals. What I think we need to do is get the methods. I think the future is the chemometric methods being embedded in the software, so you collect a bunch of samples and then do some broader classification that might not be as specific to drug A versus drug B, or what are the the quantities of certain elements in metals, where instead you would be maybe I want to determine whether the origin of these drugs, and so you could build a model that could determine whether the drug is coming from Colombia or Peru or Brazil. If you look for illicit drugs, or maybe it's just like what species of tree it is, or what geographic location of where this rock came from. So there it wouldn't be these broad discrete models, but it's more user-based models defined by what's the user's specific application in mind.
So, are you aware of some of the new ideas in smart sensors, or how would you even address that? What's happening in the whole world of smart sensor, and by that, it's either a micro sensor or a larger sensor that doesn't require very much intervention. It's generating data, and then potentially there's AI or something being used to process the data and get a result. But there's not very much in terms of human interaction with that.
I would love to learn more about what's the state of the art that's going on with that, because I think where it could go, is not just doing exactly what you said, but the sensor could also be smart enough to change how it does the analysis based upon what it sees initially. It might do like a prep analysis and then changes the way it operates to do its final analysis. It might be adjusting, intensities or extractions or any other parameters that could be adopted. So I think, but to answer your question, I'm not as up on that as I really would like to be. I'm hoping a lot of this stuff will be covered in the NSF workshop, because I know I brought in a number of people who actually, who at least I believe, are much more close to the cutting edge of doing smarter sensors than I've been doing.
Well, thanks for that answer. Just again, moving into a subject that you talked a little bit about is, do you think there's any controversy surrounding basic discussion of the use and limitations of chemometrics? Are chemometrics limited in their ability to address data?
Yeah, I if anything is the limitation that I see is the vast majority of the chemometrics models, and I don't want to go so far as to say all of them, because someone will come up with one or two that will prove me wrong. But for the by and large, all of the models, the methods are more inferential when it comes to the science than they are explicit. In that these aren't models that are based upon a first principle analysis. It sort of looks at it, takes collected data and builds models, oftentimes based upon correlations or other correlations, effectively, where the parameters in the models do not represent a physical reality. They're descriptive more than they are determinate. The parameters are descriptive. They're not deterministic. So that is where I think the limitations are with chemometrics, is that you're not building first principle models. You're building topographical models, more the ones that describe a surface, that describe what's going on. They don't define what's going on in terms of the parameters aren't physically meaningful. I'd love to be able to do more of that, but in a way that's kind of outside the realm of chemometrics, and that the chemometric thought of being more data driven than first principles driven.
Interesting. Karl, here's a follow-up question. What are the real constraints in using and interpreting chemometrics? And then here's the catch, or other data analytics techniques for making major policy decisions or for politicizing science? we often hear that's the science. But as scientists, we know that the mathematical analysis can only disprove, it cannot prove.
Oh, yeah, we could talk about this one for a long time. Um, two major things that drive me crazy, and I really try to harp on this to my students. One of them is extrapolation, is especially with the models that are more inferential, they really don't extrapolate well, and especially if there's any kind of nonlinear terms. And there's way too much that's being done, I fear, on extrapolation. And that's even before we get to p-hacking or cherry picking your training set. um, the other thing that I think is that the thing that I think is a major underappreciated issue is whether is the recognition of what are the inheritance assumptions of the models that we're using and of the data, and what are the consequences if the data does not follow the assumptions. And we really have almost all the methods we do have a basic assumption of a normal distribution of errors or a normal distribution of parameters. And unfortunately, the world is not normally distributed, and so many of the processes, especially on the political, geopolitical um, tail or spectrum, are driven. The consequences are driven by the tails, not by the majority of the data. For example, the whole it at the risk of I think it's become more and more accepted now that the savings and loan market crash, the housing bubble crash, was largely driven by the fact that the models of market stability did not account for failure on the tails. And that's where we got the whole concept of too big to fail. Because if a company is far enough along the tail that they're not part of the normal distribution of company size and company performance, the model fails. And there could be the same thing going on with chemistry. I remember reading a paper years and years and years ago about they were doing some analysis. It was actually a spectroscopy analysis of enzyme performance. And what they found was a lot of the performance was driven by a few super enzymes in a population that really had a much greater turnover rate than the bulk. So yeah, there was the majority had a um, kind of a normal distribution, but the actual performance was governed by the fat tail, the few enzymes that were, super enzymes, not the ones that are just kind of average put together, might be one or two standard deviations away. So I think that's kind of what we don't appreciate and don't worry enough about is what are the consequences of deviations from our assumptions.
That's a fascinating topic. Um, in one of your grant proposals, you introduced the concept of the Center for Adaptive Networks, sensing the environment, and you named it CAN-C. Could you explain to the audience what was the meaning of this or the purpose of this center?
Yeah, this is something I really wanted to get funded, and unfortunately, I'm not smart enough to know how to navigate the funding landscape to get it done. In that I know what the big picture is, but I don't know how to get there incrementally. So it the concept, to my mind, is rooted in something that might be familiar to a lot of gamers these days: foveated imaging. So it's named after the fovea of your eye, where it's the process that the center of your eye has much higher spatial resolution than the fringes of your eye. So in other words, where you're actually looking, you do that at high spatial resolution. And then at the fringes, you just get low spatial resolution in order to kind of get an idea what's going on. But then you focus in on where you're doing things. And that comes into context with gaming, especially with virtual reality, where they do foveated imaging. They track your eye to see where or foveated rendering and imaging, track your eye to see where your eye is looking on the playing field, and they spend the computational power to do that area at high resolution. And they don't need to worry about the other areas at lower resolution because they're not as important. Just enough so you see what's there, so your peripheral vision, but not enough to where it sucks up all your computational power to render that. Okay. So with that as the backdrop, I got to thinking, we really need the same concept with chemical sensors to develop, to study the environment, study exploratory analysis, maybe for homeland security, where we might have some sort of chemical threat, where we have a large area of processes that we need to monitor, where the chemistry changes in time and in space. And if we could have a swarm of, we'll just start with a swarm of low resolution chemical sensors. Each one might be the equivalent to a rod or cone in your eye, or a pixel in foveated imaging. But now we can dynamically, by having them all talk to each other and communicate, move around where they're sensing the environment, where they find sense anomalies, places of interest that might be where chemistry is happening or interesting chemistry is happening. They can start to swarm around that better to get that at a higher spatial resolution. Whereas the rest would always kind of form a more diffuse halo around it to keep looking around where, in case other chemistry happens to pop up. Now, throw onto this, and the other analogy I have is a blue water navy, where they have a bunch of different ships. We have everything from capital ships, from aircraft carriers, which are few and far between, but very expensive, but extraordinarily powerful, to more agile but less powerful things like submarines and destroyers and specialized things like submarines or mine tenders. So if we have a number of these sensors that take part of the swarm, where you could have the swarm start moving these more specialized sensors around to do analyses, and maybe even the output for some of the sensors would inform and modify how other sensors would act, how they would do things. And what I mean by this is, imagine if your inexpensive sensors, your cheap swarm, finds a place that's chemically interesting, calls over the bigger sensors. The bigger sensors go there and realize it's chemically interesting, and the chemistry is different from anything we've seen before. It could, meaning there's an interference, it could do an analysis and come up with a way to recalibrate the swarm to account for this interference. And now the swarm becomes more efficient. While at the same time, the swarm is guiding around the bigger sensors. It might tell it a lot about what's going on. And then that might involve the more complicated sensors to maybe change the way it's doing things. Maybe it wants to do a slower analysis at higher signal to noise, or maybe needs to do an exploratory analysis to find out what are all the possible interference that are there, or a number of different things. I might decide that, okay, I need to analyze for these 3 chemicals in my battery versus the other 4 chemicals in my battery of possible analyses. So that's the kind of whole idea of CAN-C, is that is how do we get an adaptive network of sensors that changes over time based upon the chemistry it's observing, both how it performs analysis, how it moves in space and time, and what are the the models it applies and uses, which will be a lot of, aside from our normal calibration models, but also start to bring in a lot of concepts from network analysis and maybe deep learning as it keeps retraining and remodel and refining its calibration models as it goes along.
Well, that's very interesting. We'll have to see how that develops in the future. I mean, you can even use satellite information networked into that. So,
Oh yeah, definitely. Yeah, you're right. And any kind of information that might be available, there might be, maybe there's some, if it's a ocean analysis or coastal, there might be some moored buoys that don't change, but they, in location, but they could be doing measurements, and and satellite for remote sensing, and yeah, all sorts of possibilities. It's basically using all of the methods that might be available to us in concert, and allowing the ones that can change or move to change or move in reaction to what the field is seeing. I mean, that's the way we work as society, right? Someone comes up with a good idea or learns something new, and everyone else changes the way they're doing, in reaction to it. Why don't we do it with sensor networks also?
good thinking. We'll have to see how that goes. Uh, how can one find really the best computer and software tools to further explore chemometrics?
Oh, um, best is tricky. Is always tricky, right? I think that depends largely on what you want to do and what your comfort level is with statistics. And so I'm at the risk of leaving anybody out. I will just kind of call out a few names. I think that programs like Unscrambler and Pirouette do a really good job. They're geared to slightly different audiences of bringing basic chemometrics, and the PLS toolbox does that also. Brings basic chemometrics to a introductory users, and almost every instrument vendor now, the big ones, have some sort of rudimentary chemometric software on their capital instrumentation. They're good instrumentation. You can get some version of Unscrambler or Grams or something that does PLS and cluster analysis, that stuff. The next level is now when you're wanting a little more flexibility and want to start to maybe move. Well, so those methods I talked about before are basically, to me, they're almost just like a paint by the numbers. Where you're really constrained to what you can do. They make it so you don't break things, and they do it well, but you only can do what it's programmed to do. They're more or less rigid. Then you want to get a little more knowledge. You go for a little more flexibility. That's where something like the PLS toolbox comes in, where they have both their graphical user interface software that works a lot like the other Unscrambler or Pirouette, in that it's relatively rigid, but it also has more access directly to all of MATLAB, so you can start to color outside the lines, or color things the colors you want to, not have to just follow a script. And then after that, and this is where the big jump comes in, there are tons of packages in R and Python for machine learning. And these are a lot of things that haven't quite made it into the PLS toolbox, or Unscrambler or Pirouette, where if you are able to kind of be a little more savvy with higher level programming and accessing, doing things a little more on your own, you could then start to use more cutting edge machine learning tools and modify how you use those to augment your chemometrics, your chemical knowledge, your domain knowledge. And now really then you become almost, a chemometrics researcher. Yeah. So it's kind of the whole continuum. So where would you find them? I think it all depends upon where your comfort level is um, for doing things. And also, and I mean, I guess it's more the comfort level is often I use PLS Toolbox and the more rigid programs often because sometimes I just want to do basic methods. I don't want to have to, program everything from scratch, so to speak, in R or MATLAB. And it's just really easy to throw things into one of these established toolboxes, and it gives me all the plots that I want, and they all look pretty, and I can send it off to someone that's interested on the results very quickly. But again, if it requires more outside the box analysis, then things like R and Python with their toolboxes are the way to go.
Well, thanks for that information. What are some of the best literature sources for our listeners? Where can they go to find the information on this type of topic?
That's a hard one. And I guess again, it all depends um, on your comfort level with the different methods. Um, Applied Spectroscopy, the magazine, well, your magazine Spectroscopy has a lot of user based or more a lot of good application basis. So in other words, it's more application driven in how they use chemometrics to solve problems versus articles, journals like the Journal of Chemometrics, or maybe some more, IEEE journals on machine learning, where they talk more at the higher level about the statistics and the models and the methods, and less about the applications. Yeah, so it's hard to find I think it's hard to me. It's a hard question to where to point anybody in that because I'm not confident there's a good universal source because I guess it depends so much upon someone's implicit knowledge level and their applications. Are they trying to do things that are well established in just a new area, or are they trying to solve problems that no one solved before? And the literature is just so darn fragmented, which sort of comes back to one of our earlier conversations of what's wrong with the review process, um, and by making things being more outcome based or product based, we get a fragmented literature, so it's really hard to find concise sources of ways to help solve problems. So there's an entirely unsatisfying answer to that question.
So what do your students do, the new ones, the students just coming into this?
They spend a lot of time reading the literature. Um, so we do a lot of, a lot, and the students, I don't know, they oftentimes come up with ideas and methods that you know, I might not be familiar with in the literature, and they come up with ideas from what they're reading. Um, a lot of, I guess, in a way, chemometrics hasn't evolved that much in the last 30 years that I've been doing it, 40 years, because we started off as a bunch of thieves. Um, in that we stole almost every idea we had in chemometrics from statistics or psychology, and I mean it worked, right? Why stop? So we just keep your eyes open in the machine learning literature, statistics literature, looking at methods that work, and they steal them and apply them to new things. I got a bee in my bonnet right now about network analysis. I think there's got to be lots of good applications for network analysis in chemistry. I haven't figured out exactly what they are yet, but I'll be darned if I don't want to be one of the first persons to use them. And so I'm kind of trying to come up with right ways to do that. We got a paper that just came out using it for visualizing confusion matrices in for classification models. It's a special issue of the Journal of Chemometrics dedicated to Steve Brown, who just retired. So that's kind of where just, troll the literature, keep your eyes open for other methods that just might be able to be applied to something chemical.
Well, thanks, Karl. Can you give us some wisdom? Could you share with us some wisdom that you've received over the years on analytical chemistry and things you've gleaned over the years? Just a sentence or two.
I guess the major piece of wisdom that I have is really think about how you're going to analyze the data before you collect the data. This because you asked earlier about experimental design. There's so much that relies upon appropriate experimental design, and that's just not which samples you collect, but are you collecting enough of them? Are your instrumental parameters set up right so you see a good difference? Is the difference larger than the noise? If not, how many samples do you need to average to get the signal to noise right to see a method? This might be maybe I'm just remedial, and this has always been incredibly obvious to other people. But when I started teaching statistics more and more to my undergraduates and into the graduate class, I never realized how much of statistics, just the regular t-test, really is describing signal to noise. And it's in there. It's directly signal to noise ratio. And so so that would be the thing that I would think of. Just when you're doing an experiment, whether it's something quantitative or qualitative, get a feeling for what effect you're wanting to see, what's its magnitude, and what your noise is. So really, what is the signal to noise that you need to see the effect or see the outcome that you're really designing your experiment to observe? That you can't overestimate signal to noise enough. Well, you probably could, but it's hard.
Okay. Well, that's a good place to close. So thank you, Karl, for this informative and lively discussion on your work. I'm sure our audience has learned a lot about recent developments in miniaturizing sensors for analysis and all the corresponding chemometrics and data analytics related to this topic. And your thoughts on this subject have opened my mind to many new possibilities in analytical sensing. My thanks to all of our listeners and production and editing team that has worked to make this podcast possible. We invite our podcast audience to stay tuned for our next informative Analytically Speaking episode. And remember what Albert Einstein once said, we cannot solve our problems with the same thinking we used when we created them. Have a great day.